The forest, one of the few natural resources of this remote northern country. Wood provided the basis to build a civilized society here, long before anyone dreamed of electricity or running water. The forest yielded the raw materials for the industries that established Finland's prosperity, but it can also shape our future. I'm Howie Jacobs, a British molecular biologist based in Finland. In this episode, I'll be taking a journey with you across Finland and beyond to explore how our forests can sustain our economy and promote welfare. Most people assume that transportation and the generation of electrical power are the main sources of CO2 emissions. But in advanced countries like the US, for example, transport accounts for only a third of CO2 output. Surprisingly, it's buildings that are the main culprit, producing almost half of all emissions.
The way I think about it is that we have two major existential problems to solve as architects, as builders of shelter. One is the fact that what we build has an enormous carbon footprint. The making of it has a carbon footprint. The operating of it has a huge carbon footprint. The next problem is the world has roughly 7 billion people. 3 billion people are expected by UN Habitat to need a new affordable place to live in the next 20 years. We're going to be building a lot of buildings. If we build them the way we have been building them, we're on a collision course.
Could something as simple and familiar as wood help us address the linked challenges of urbanization and climate change?
Wood is the only material I can build with that stores carbon and stores it in the building for as long as I keep that building from burning or keep that building from rotting.
Wood has been used for centuries to make buildings and furniture in almost every culture on Earth.
But it became to be seen in the 20th century as being rather old-fashioned and more associated with poor people and peasants.
However, over the past decade, a renaissance of wood has begun.
And part of that renaissance has come about because of engineered wood products. Things like cross-laminated timber and glulam beams and laminated veneer lumber. And all of a sudden, I think architects realised there was huge potential for these new materials, and some really stunning buildings have been created out of them.
It's, I think, the most sophisticated building material known on Earth to build big buildings. And the difference is, its sophistication is it's not man-made, it's naturally made. It's designed by nature, it grows by the power of the sun. It's the purest form of solar energy to make through photosynthesis an organism that, a tree as it grows, that's giving off that oxygen and soaking up the carbon dioxide. And in turn, as designers and architects, we now understand the strength of that material with either in its raw state, just a tree, or in engineering it and gluing it together. It can be profoundly strong, and it can do things we're only beginning to realize.
Engineered wood opens up new possibilities for large-scale building projects. The idea is to improve the natural properties of wood whilst reducing the ones that are less useful.
Insinööripuu on tietysti sit niin kuin lujempaa ja sitten jäykempää kuin mitä tuommoinen tavallinen metsässä kasvava puu on. Mutta tietysti siinä niin kuin on luonto on pitkään aikaan kehittänyt tätä tuotetta ennen meitä. Se on tehnyt tuotekehitystä niin sanotusti. Ja se tulee sieltä sen perusominaisuudet ja sen jälkeen voidaan sitten vielä pyrkiä parantamaan sitä erilaisin toimin. Puussahan ei ole mitään muuta vikaa muuta kuin, että siinä on oksia. muuten se on ihan hirvittävän hyvää tavaraa, mutta ne oksat heikentää sitä, kun ne on vetopuolella rakenteessa, se oksa ei kestä vetää niin hyvin. Ja sitten jos nyt edetään sitten insinöörimäisempään puutuotteeseen, esimerkiksi meidän kertopuuhun, niin siinähän me nyt sitten tehdään pilkotaan se palasiksi ensin se puu, ja sen jälkeen liimataan se takaisin yhteen niin, että se oksa ei olisikaan samassa kohtaa koko ajan, vaan että me saadaan se oksa eri kohtiin, jolloin meillä on vain 3 milliä oksaa sitten yhdessä kohdassa.
LVL, laminated veneer lumber, is made by bonding thin layers of wood together under heat and pressure. This creates a strong, durable and uniform wood product. Depending on the orientation of the layers, it can be used either for panelling or as structural beams. Metsä-Wood's Kerto LVL has been used to build the world's first wooden wind turbines, as well as the largest wooden structure anywhere on Earth, the extraordinary futuristic Metropole Parasol. The global challenge of rapid urbanization places huge demands on the construction industry. We need to build faster and in greater quantity than ever before. One answer to the need for prefabricated components is cross-laminated timber, CLT. In the first CLT factory in the Nordic countries, located in Kuhmo, entire flats, including domestic appliances, are pre-assembled in the factory. I visited Austria, where Finnish company Stora Enso is turning locally grown spruce and pine into this robust and versatile product. So is this what we're actually looking at here?
Yes, we use first layers in this direction, then crosswise layers. We glue it together, and that makes it extremely stiff.
Okay. What are you gluing it together with?
We glue it together with polyurethane. It's formaldehyde-free glue, and then the wood doesn't make cracks and doesn't cross. And we make it from 3 layers to 7 layers, different thicknesses.
Norway has acquired a taste for using CLT in large-scale building projects. Here, wooden houses are no longer mere fishing cottages, but sleek apartment blocks where concrete slabs, beams and pillars have been replaced by CLT. Wood is certainly a stiff, lightweight and resource-efficient construction material that is easy to assemble on site. But its virtues go way beyond a low-carbon footprint. In Trondheim, for example, 9-story wooden buildings were erected in just 4 weeks.
7, 8, 9. 3 floors more.
3 left.
Okay.
While wooden high-rise buildings are popping up all over the world, Finland is lagging behind. After Spain, Finland builds the highest proportion of multi-story buildings of any country in Europe. Yet, they are mostly not being built out of wood. So, why aren't we using wood in Finland to make high-rise buildings? So why aren't we using wood in Finland now to make large multi-story buildings?
Itse asiassa nykyisin rakennetaan, mutta meillä on Suomessa nyt piirtynyt semmoinen käsitys, että puu on vapaa-ajan rakennusten, pienimittakaavaisten rakennusten, pientalojen materiaali. Ja sen takia tarvitaan nykyisin hyviä esimerkkejä osoittaa, että puu on ihan kilpailukykyinen rakennusmateriaali myös suuren mittakaavan rakentamisessa. Esimerkiksi 2 teollisesti tuotettua suurin mittakaavasta rakennusta hyviä esimerkkejä on Pilketalo Rovaniemellä, Metsähallituksen rakennus. Pilketalo alitti kustannusarvion jopa 500 000 €. Ja omalla esimerkillä on Metlatalo Joensuussa.
So what is holding Finland back from developing a proper wood construction industry?
Tällä hetkellä me tarvitaan puumyönteisiä rakennuttajia, rakennusliikkeitä. Ja rakennusliikkeellä on se ongelma, haaste, että ne vertaa koko ajan siihen, mitä ne on tehnyt viimeiset 60 vuotta. Ja me tarvitaan uusia avarakatseisia rakennusliikkeitä.
A major obstacle to developing large-scale wooden construction in Finland has been national legislation. Regulations have improved, but there is still some way to go before wood is treated equally with other building materials. At the Stora Enso Wood City site in Helsinki, a number of new wood products have been tried out.
CLT:stä tehdään suoraan seinärakenteita ja taas niin kuin pystykantavia seiniä ja yhtä lailla holvirakenteita, että saadaan koko esimerkiksi kerrostalon runko tehtyä täysin puupohjaisesti, niin se on niin kuin muuttanut nyt sitä lähtötilannetta, mitä minun mielestä vakavasti ottaen ei ole tähän mennessä ollut.
Introducing new products into a conservative industry simply takes time.
From our perspective, it takes a while for a certain market or country to really learn to use those products. And how we work is that we seek partners to work with us, to grow with us, and to kind of spread that new way of building.
A total transformation in our thinking about buildings is needed. In many ways, it recalls the paradigm shift that occurred a century or so ago with the advent of the first skyscrapers.
And in 1885, as I talk in my TED Talk, a building was built in Chicago that became what we call the first skyscraper, and it was 10 stories tall. And people were terrified to walk underneath the building. It seemed so scary, so tall and so scary. But only 4 years later, the Eiffel Tower was built, and Gustav Eiffel built it, and it's 300 meters tall. It is the equivalent of 90 stories tall, depends how you measure it. So we went from 10 stories to 4 years later to almost 90 or 100. And it changed the way we built to this day. Every major city on Earth was informed by this movement to go high. Today, we're in a whole new era. It's not the Industrial Revolution, it's the climate revolution. It is about how we build for the next generation, and it's about a systemic change. And what we need, therefore, is a new Eiffel Tower moment. And it's going to take breaking through the height and building in a new way, and building and proving that it's possible. If we change people's understanding of what's possible, the world changes. And that's the real art and beauty of an Eiffel Tower moment.
All the cities, including Helsinki, are building higher and higher. So we just don't survive with building small buildings. So we have to develop the technology. In past 10, 15 years, we have lived the most interesting period of wood construction. Because starting from, in Finnish scale, from 2-story buildings, we have built up to 14, and globally the tallest wooden building is at the moment 25 stories high.
New engineered wood products are making this a reality. But apart from enhancing strength and durability and protecting wood from rot, sunlight and extreme weather, fire resistance is essential if we are to create safe and long-lasting wooden buildings. While some established methods for fire protection are effective, they're based on materials harmful to health, both in their initial use and at the end of their life cycle. Novel, environmentally benign methods are emerging from research labs, often inspired by centuries of tradition.
Ja tämä luontainen harmaantuminen, niin tämä on niin kuitenkin se yksi kestävimpiä pintakäsittelyjä. Et meillähän on niin kuin esimerkkejä satoja vuosista vanhasta harmaantuneista taloista.
Many things what people have used in built environment in several centuries ago, those are still valid now. Earlier we didn't use any paints, but still some 1,000 years old wooden church is still standing in Norway.
At Aalto University, the Wood Material Science Group seeks to improve wood by methods that permanently alter the cell wall structure. Wood modified in this manner is not treated with any biocides, so remains non-toxic throughout its life cycle.
Basically, there's probably 3 different types of modification. There's what's called a chemical modification, which is a reaction with the wood. Most famous example of that is acetylation, and we have a product called Accoya, which uses that technology.
Acetylation has been known for more than 80 years as a way of making wood more resistant to humidity. In the Accoya process, acetic anhydride is forced into the plant cell wall, converting free hydroxyls to acetyl groups, thus reducing the wood's ability to absorb water.
Then we have what we call impregnation modification, which is basically you put something soluble in the wood, you polymerise it and it stays in the wood, but it has to go in the cell wall, otherwise it's not a modification. And then we have thermal modification, which I think Finland's led the world with thermal modification, where basically you heat the wood but in an environment where oxygen isn't so readily available, so you don't really want to set light to the wood.
Although these modified wood products are already on the market, we still need to determine the exact effects at the cellular level.
And I've been working with wood for 30 years now, and I probably know less than when I started actually, but that's the nature of wood.
Although these modified wood products are already on the market, we still need to determine the effects at the cellular level.
We know for more than 100 years that it takes up moisture. But even like more than 100 years later, we do not know the exact reason of this fundamental aspect of wood, why it takes up moisture and releases it again, why there's the hysteresis between absorption and desorption, so in different fields.
The exact nature of the interaction between water and wood remains largely unexplored. The water in wood is linked to all of its properties, so understanding the interaction is essential if engineers are to manage these properties and extend the lifespan of wooden products.
The worst enemy for wood is always water. So that's why our group is concentrating on wood and water interactions. We need to study how water molecules are entering in wood, in which locations they are entering in the wood. Is it in late wood, early wood, or cell wall level?
What we know is that wood keeps exchanging water with its surroundings. So we need to understand quite to the fundamental level how wood and water are interacting.
If wood takes up moisture, the strength drops, it decreases. It's also associated with dimensional changes, swelling and shrinkage, which typically we do not want. Or if it's even for longer period and quite wet, particularly in outside applications, then it can also be decayed by fungi. And this is something that we should prevent, like I said, as effective, as efficiently as possible. So it's really important to understand the process of water uptake and release in wood. Why does it take up moisture? What is the mechanism behind that? We do not really know that in detail.
Mohammed Arwais at Aalto University has combined computational modelling with imaging to profile the distribution of chemicals in the wood. This can guide the development of new treatments to improve wood properties.
We can see those changes and we can develop an efficient treatment method that can be more homogeneous and improve the overall quality of the wood in several other outdoor applications.
Wood can play a major part in mitigating the daunting environmental challenges we face. So, a better understanding of its properties and behaviour will help us to use it in the most effective and sustainable way. Apart from understanding wood after it has been harvested, we also need to appreciate how a living tree works and how we could engineer it. This is where biotechnology comes into play. Imagine if we could substantially accelerate the growth of trees, or grow them in arid environments, reforesting whole areas on which hardly anything at all grows today. Or if we could improve all the properties of wood that make it so useful in the construction industry. The starting point for doing any of these things is to understand the genome and how it programs the biology of the organism. In a major undertaking, Yrjö Helariutta and his team have recently analysed the full genome of the birch. The genome, plus a panel of relevant genetic variants, make it possible to identify the genes that control the way the tree grows. The genes which control plant development and specify the formation of the vascular system are basically the same in all plants. So, by using the model plant species Arabidopsis, equivalent to the fruit fly for plant biologists, we are able to speed up discovery. We can translate knowledge obtained in a plant like Arabidopsis, which grows to maturity in a matter of weeks, to much slower growing species like trees that take years to reach maturity.
If we think about trees, so this would take, I would basically ask my daughter to wrap up these experiments.
Long after your death.
Right. But in Arabidopsis, the generation time is, rather than tens of years, it's like a couple of months.
Even though it's only a tiny little weedy plant of a few centimeters in height, it nevertheless is making the same constituents that go into making wood in trees.
If we would really understand the wood formation process in depth, we might, in Arabidopsis and trees, we might be able to create Arabidopsis, which is actually looking like a tree.
Okay, that's an interesting concept.
Kasveissa liturassa me ymmärretään jo aika paljon, miten geenit määrittelee tätä oksakulmaa esimerkiksi. Ja on näytetty, että myös puussa oksakulmat määritellään hyvin samalla tavalla. Me voidaan käyttää tätä lituruohoa jossain määrin mallina myös puun tämmöisen arkkitehtuurin ymmärtämiseen.
But then you can use that knowledge in the future to engineer the properties of the tree plant.
Me voidaan periaatteessa saada puut kasvamaan nopeammin, jolloin me saadaan ne tehokkaammiksi hiilinieluiksi tai sitten me saadaan enemmän biomassaa. Toinen vaihtoehto on jalostaa puun laatua. Esimerkiksi niin, että me halutaan vahvistaa sen soluseinän rakennetta, siitä tulee parempi esimerkiksi hiilinielu.
In the future, genetics and gene editing will offer us ways to customize the properties of wood and even the rate at which trees grow. The more we learn about trees, the more we can use and modify their properties for human benefit. One of the less studied benefits of wood has to do with human well-being. Finns know what it's like to sleep well in a wooden cottage. We like the look and the feel of wood in our surroundings. But why is this? Are there sound physiological reasons for this preference? I went to visit Mark Hughes, Professor of Wood Technology at Aalto University, to learn more about how wood modifies the environment in buildings in ways that impact health and well-being.
When the atmosphere is moist, the wood absorbs moisture.
And when it's dry, it releases it back to the atmosphere.
So it has an effect of buffering, so it evens out the internal climate. So it affects people's comfort levels. Like with this piece of wood, the moisture will absorb much more quickly in this direction along the grain than this direction here.
Okay, so you have that facing into the room, as
exactly,
it were.
Exactly.
That's much more effective than having the logs placed longitudinally like wood, a more traditional usage would.
Yeah. If you, for example, touch the surface of this one.
This natural moisture buffering effect is the main reason why neurosurgeon Takehiro Maeda chose Finnish pine logs as the construction material for his clinic, located near Tokyo.
御殿場という土地は非常に、特殊な気候で、湿度が非常に高い場所なんですね。で、鉄筋コンクリートで、苦労したのは非常に結露が多くて、それで低いとこから湿った空気が来て、で当然結露が多いわけですね。鉄筋コンクリートっていう建物は非常に密閉性が高い。
Dr. Maeda built the very first wooden hospital in Japan.
やはり最初役所に相談に行った時に本当にログでやるのかというふうに何遍も向こうはびっくりしたというのが本当のところだと思います。
The Finnish supplier, Honka Rakenne, had to face many hurdles.
やはり本家はやっぱりそういう耐震性だとか、それから火の問題ですね、火の周りの問題だとか。
Kyllä siinä tietysti välillä usko meinasi loppua, että siinä on niin paljon säädöksiä, byrokratiaa, ja uskomuksia, että puu palaa tai puu mätänee tai ei kestä kosteutta. Ja me osoitettiin kaikki yksi kerrallaan kaikki kohdat, että näin ei ole.
そういうことで、そういうことを役所に示して、役所の方が納得したということがあったと思いますね。
The hospital in Gotemba seems to provide more comfort for patients. But can we actually measure scientifically the effect of wood on human health? There is rather little hard research on this topic as yet, but Japanese scientist Yoko Tsunetsugu is one of the pioneers of the field.
私たちはこのような木をたくさん使った居住環境が人の心と体に与える影響を調べています。それで例えば木の匂いを嗅いでもらったり触ってもらったり、木のお部屋にいることによって血圧とか、脳の活動、それから心拍数がどういうふうに変わるかというような、そういうような測定をしながら研究を進めています。そういうある種の木の匂いですとか手触り、それから見た感じっていうのがすごく実際に体にリラックスさせるような効果を与えている。光を脳の中に入れて、それで血流を測るような測定法があって、NIRS と言われている手法ですけれども、それからあとは血圧を測ったり脈拍数を測ったりするのは、それを指で1秒ごとに測るような、こちらも最新の方法を使って研究をしています。
One of Dr. Tsunetsugu's interests is alpha-pinene, which is found in hinoki, the Japanese cypress, as well as in Scots pine, which is abundant in Finland. It protects the wood against insects and creates the scent that we all recognize.
いまして、そのようなことからも生理的な状態を動かす作用が匂いには手触りとか見た目に比較すると強いのではないかというふうに今のところは考えています。
As the world struggles to cope with the unprecedented challenge of the climate crisis, forests play an increasingly important role in the equation. But making full use of them without undermining biodiversity presents a major problem.
I think if you ask 200 people what sustainability is, you'll get 200 different answers. We know what a sustainable yield is if we take a sustainable yield from a forest, or we take it from a farm, or we take it from a fishing ground. It's basically what we can take for our own use without compromising the ability of that resource to regenerate.
We have to respect the limits of the forest, and where do those limits lie? Is it to do with the amount of material that we can take within the annual increment? So we're just thinking in terms of the forest biomass, or do we also need to think a little bit about what actually the forest is for? I mean, it's not just there to provide material, it's also there to provide ecosystem services, it's to maintain biodiversity. And I think this is becoming much more prominent now in kind of discussion, that we have a biodiversity crisis, we have a climate crisis. Okay, what on earth do we do with these? We have to look at it in a very systemic way.
Solving these challenges also opens up new opportunities.
Now is the transformation. If I could invest all my possessions into sustainability as such, I would do it in a heartbeat, because I have 110% faith that whatever the businesses are that basically put everything into sustainability, they will also be profitable.
The Finnish forests have undergone massive change over the past 200 years. While Finland has seen significant reforestation over the past century, many countries in Europe have experienced deforestation.
I come from the UK, where we had a pretty bad track record when it came to forests. I think we got our forest cover down to maybe 5%, maybe less of the whole land mass. I think we're up a bit higher now. And that's basically because we didn't value the forests. And they're not really part of our culture, and also I think we industrialised pretty early on. And it was all about productivity, and a forested piece of land was just seen as being a wasted piece of land.
Today, more than 75% of Finland is covered in forest, making it one of the most forested countries in the world. Finland has 5,000 trees for every single inhabitant, and most of the annual forest growth of 100 million cubic meters is actually harvested. So not surprisingly, forests play an important role in Finland's economy. The sector accounts for over 60,000 jobs and 4% of GDP. But a significant part of Finland's forests are protected and excluded completely from commercial forestry. When used wisely, forests can serve a triple role: a carbon sink, a source of renewable raw materials, and valuable habitats for countless species. As global climate change and biodiversity loss accelerate, the sustainability of forest use is under constant review. Tuula Jyske from the University of Helsinki has conducted extensive research on the potential of wood.
We could harvest less and use more wood for added value purposes. So I think these are going hand to hand, that if we can create more value after harvested material, then we have more options to also leave areas of forests for that kind of management, which maintain the ecosystem services and also are good for the biodiversity.
The growth of each cubic meter of wood results in the absorption of about a ton of carbon dioxide from the air, varying slightly according to the type and quality of the wood. For comparison, manufactured wood products contain only about 1% of the amount of carbon stored in forests. One way of increasing the amount of carbon stored in wood products is to make them more long-lasting by improvements in recycling, reuse, and life cycle design.
If we want to add value and also sustainability in the use of different bio-based renewable materials, we need to think already in the beginning of the designing process, the circularity, that how we can enhance the life cycle of the products. It's called like a circular by design principle, and also somehow develop those mechanisms, market mechanisms that support this kind of circular use.
Of the total carbon sequestered in wood products, the share of buildings is estimated to be around 60%.
If 30–40% of the CO2 emissions, for example, come from the built environment, we need to find solutions how to make that more healthier. And once again, as we've seen in Denmark or in Netherlands or slowly in France and very slowly also in Finland, Sweden, UK, the legislation is the driving force. Because eventually we need to somehow regulate the amount of CO2 emissions we are releasing into the air.
What we can do is we can also look at, well, okay, why don't we use the material that comes from the building? So rather than using fresh wood that we have to harvest for, we use material that's already existing, that still has value, still has utility because it hasn't reached the end of its life. So we recycle that in a materials cascade.
Extending the life cycle of buildings and building materials is therefore of paramount importance in mitigating the climate crisis. Wood has the potential to store carbon for centuries, and this is essential as the demand for housing is skyrocketing.
So we are going to need new buildings, and we know that wood can play a strong role here.
However, there is much room for improvement in the recycling and life cycle design of wood products, especially in the construction industry.
I think in general, we, as engineers, we have a quite large responsibility about our environment. And I mean, we all know that our buildings are a large share of our CO2 footprint and other environmental burdens. And so we really should start to design our buildings in a way that's in multiple ways more efficient.
Construction and demolition create the very largest waste stream globally, accounting for almost half of all waste. Less than a third of the building industry's waste is recycled. The residue, over 20 million tonnes a year in Europe alone, is just discarded. That represents over 9 years' supply of wood for the building industry in Finland. The hybrid nature of buildings is a major obstacle for recycling wood.
Building always contains multiple materials. It would be very inefficient to have an entire building from one material, so at the end it will be a hybrid product out of many different kind of components.
A multidisciplinary research team in Aalto University is working on a whole life cycle approach to how wood is used in construction. This requires an understanding of the properties of aged and used wood.
But when we talk about a piece of wood that's been, let's say, taken from a demolished building, it will have undergone an aging process, depending upon what function it had in that building, if it was a structural member or if it was non-structural. It'll also depend upon things like whether it's had any coatings or any treatments. It will depend on how it's been fixed, whether there are any glues, metallic fixings, whether it's been made as part of a system, so whether it's got insulation attached to it or plastics. So there's a whole bunch of different things that can influence the quality of that material.
The quality should be assessed, and there are many applications according to the quality of wood, but after the demolition they crush it in smaller pieces in order to make the basically transportation to waste management site much easier, which is against what we want for use and recycling. So I would say there are many applications like CLT, LVL, like even direct reuse or particle boards or anything rather than energy recovery.
Hughes and his team also address the challenge on a systems level.
I think the whole life cycle is the key point, because when we're thinking of life cycle of product, we usually think it from the material to when we maybe dispose of it or then reuse it afterwards. But when it's wood we're talking about, then the whole life cycle is actually already, we should have a focus also with the forests there and the use of forests, which we use as a material.
Climate change is likely to cause future population displacements that will dwarf today's refugee crises. This will produce massive short-term housing demands, and these will have to be met without further drastic harm to the environment.
Esimerkiksi puusta tai bambusta tehdyissä tämmöisissä väliaikaissuojaissa, niin sen hiilijalanjälki on vain noin 5% siitä, mitä jossain sitten taas teräs- ja muovisuojassa. On hyvin iso hiilijalanjälki. Tämä on asia, mitä ehkä ajatellaan, että no eihän sen oikeastaan mitään väliä. Että jos ne ihmiset pelastetaan, niin so what? Tässä pitäisi kohdata se, että hei, että me tiedetään jo nyt, että miten me voitaisiin tehdä tämmöisiä väliaikaisen asumisen ratkaisuja, mitkä on ympäristöystävällisiä, jotka ei kiihdytä niitä syitä, joiden takia ne ihmiset joutuu jättämään kotinsa.
One of the biggest problems we have as a world when we have a major disaster, and we know we will have many more, especially because of climate change, is that we don't have a model where we go in and provide temporary shelter that's actually permanent.
In an experimental project called Paracity, the team of architect Marco Casagrande has conceived a CLT lattice that can be assembled without tools by a local community incorporating recycled materials.
Siinä tehdään pelkästään primäärirunkoa. Ja se tarkoittaa sitä, että kaikki muu voidaan tehdä siitä ympäröivästä jätteestä tai romahtaneista taloista. Kaikki se, millä ei ole kantavaa merkitystä. Et me huolehditaan siitä, että se kantaa, mutta kaiken muun porukka voi rakentaa itse.
Already about half the world's population live in cities. If this trend continues, as most forecasters expect, we'll need new homes for about 3 billion people in the next 20 years.
Ihmiset muuttaa enemmän kaupunkeihin ja on rakennettava uusia koteja, jotka on ympäristöystävällisiä. Tähän tarvitaan puuta.
Siellä on ihan uskomaton mahdollisuus Kiinassa esimerkiksi. Kun se väestön määrä on niin valtavan suuri, niin ne kertoimet on niin paljon erilaisia kuin Suomessa.
Ja vaikkapa Pakistan. Siellä on 200 miljoonaa ihmistä, keskiluokkaistuu koko ajan ja tälle keskiluokkaistuvalle väestölle tarvitaan lisää taloja, lisää kaupunginosia ja lisää kaupunkeja. Ja kun voi istua auton takapenkillä, joka ajaa 15 minuuttia suoraan eteenpäin Islamabadissa. Molemmin puolilla on tontteja, missä on jo vaikkapa vesijohtoverkot ja muut valmiina, mutta sinne pitäisi toimittaa taloja, kouluja, hotelleja, sairaaloita, ihan koko hoito. Ja se päättyy sellaiseen kysymykseen kuin, että can you deliver? Ja tässä on semmoinen mahdollisuus suomalaisille, että pitäisi sanoa, että yes we can. Että kyllä me voidaan tuoda tänne 400 000 taloa tonttiin. Niin sitten se paikka on siinä. Ja noita paikkoja on Islamabadin lisäksi niin aika paljon.
For Finland, with both the resources and the technology to make it happen, building the future out of wood doesn't just provide an opportunity to reduce the carbon footprint of the construction industry. Wood as a material also has other major advantages in terms of its properties, such as tensile strength, rigidity, and lightweight. It can also contribute to human well-being, as well as to the efficient use of resources, and to the circular economy in a way that no other material can. Whilst the forest industries branch out into new concepts and applications, wood itself must be the trunk of the new economy.
And climate has to be solved by building professionals, architects, engineers, planners, contractors, developers. We are the industry, I believe, most responsible for the largest quantity of physical things on Earth. So climate has to be addressed, and it means changing at a systemic level across the board how we think of the future of building.